I want to measure the phase stability from input to output of this amplifier, which can be an oscillator by applying feedback to it. I'm using this tiny PFA to measure the phase shift, but there are some stability problems. This is over 2.5 hours, and you can see the variations which is causing the phase noise that I want to remove from my amplifier. But these things that vary over hours must be caused by temperature fluctuations. And there are not many things involved. It's just these two cables, the two attenuators, and a power splitter, which is just cables connected in parallel as a T-connector. So phase shifts due to different temperatures of cables at different places is not going to be here. But the tiny PFA itself could cause something. So I changed the air circulation around it by placing this sheet of paper on top of the unit. And it was about here, and we'll see if it makes a big difference. Right now the steepness of the curve is higher than it has ever been before during these 2.5 hours. Right now I have removed that paper again, and they will take 6 minutes before this period is finished, because I asked for 3 hours, so it will stop then. The phase difference looks more ugly from here when I placed the paper until here when I removed it. Then it goes up. It is not quite clear cut, but it must be because of my actions that this is so different from what we see here. I have placed the tiny PFA on a bunch of aluminium. So I have it on thick aluminium, and that is to increase the thermal time constant. And then I put a frame around it from foam plastic. The wrenches are to hold them in place while the glue is hardening. And the foam plastic is to reduce air circulation, so the temperature inside of the tiny PFA will be more like the temperature of the aluminium, which should change slowly only, and with a small effect of circulations in the air that change when I come and go to my chair at the side of this table. As expected, the start here, while I'm still having my hands on the system, doesn't look so nice, so I will remove that and restart. Before doing so, I just show the difference in the Allen deviation, while this very bad result is because I'm still putting the wrenches on place and so forth. So I kill that file, delete, and I start again, like that. And Allen deviation comes rapidly, and it looks normal to begin with. And phase difference comes very slowly. You see a little red start. If I magnify it, it looks like this. The phase is drifting rapidly still. So I will make a new restart fairly soon when the speed has slowed down a little bit. Now, after a little more than half an hour, it seems that the temperature is reaching a stable value. So, first I look at the Allen deviation. It's interesting to see that the higher frequency components up to about 0.1 Hertz are the same, but at longer times the Allen deviation is much degraded. So I skip this track and start again. And now it's late in the evening, or early in the morning rather, so I will leave this and look at it tomorrow. It seems like it took a little bit more than 1 hour to reach a constant temperature, and then it has stayed constant. Perhaps now the unit has been idle for about 8 hours, so I start it again. But since it has been idle, and then I started, the current consumption in the unit will increase. So maybe it will take some time before it gets stable now also. Well, after initial instabilities, it looks fairly stable. So I will stop and restart on the unit that is warm and running. So I go here and stop, terminate, and then start again. And I delete this red trace, which was when the aluminium was fairly cold and it took a long time for it to stabilize in temperature. So I have the original without the aluminium, and then the red trace, which is cold start, and now it is warm start. And forget about the nodes down there. I can look at the Allen deviation and can see that the new measurement I'm just starting comes as the green trace here. And of course, the very fast variations, that's noise, that is the same for all of them. But then we come to the stability region here. Well, this will run now for 3 hours. The blue trace is without the aluminium and the wind shields, and the red trace is what I have obtained now. There are variations at a time scale of about 500 seconds. I just wonder whether air circulation could cause differences in temperature between those cables. So I will check for that. I recorded the blue trace before I placed the tiny PFA on aluminium. I will remove that. This way I expect the temperature on the cables to be the same. The blue was the first recording with the aluminium sheets. The second one is after I made the cables very close to each other. And looking like this, I cannot say I can see any difference. If I look at the Allen deviation, the difference here is not significant either, I think. I have changed settings on the tiny PFA, and now the phase shift versus time looks pretty good. It looks more like random noise than before. The biggest change, I think, is that I have turned down the brightness of the screen from maximum, or from very high at least, down to 0. And still I can easily see what is on the screen. I have also changed some other parameters. I have to start reading data from the unit in order to see something, so I press on acquire and then monitor. So here is what is descending to TimeLab. And here is what I see, and I haven't cleared it. It says that the phase shift
is here is 1 nanosecond, 1 picosecond, so 0.5 picoseconds. And I haven't reset it. I can do that. Null phase. And it is very stable. The signal level is 5 dBm in both ports. So this looks very good now, and I will extend the cables to start to look at the phase shift through my amplifier. Now I have a power splitter here on the signal from one of my reference oscillators, and then 2 equally long cables here, and then the device that I want to investigate is not connecting. I just have adapters here, and then a fairly long cable, both of them of equal length, into these 2 attenuators and further into the tiny PFA. Now I just started it and the phase is very unstable. It is drifting downwards here, and you see the reference. That is what I had with the old setup. And here is how the alarm deviation looks. After 1 hour and 45 minutes, the phase shift has stabilized at about minus 12 picoseconds. So I will restart and look at this tomorrow, because now it is late in the evening or rather early in the morning again. The phase is drifting slowly and linearly with time. I think this is mechanical stress in the cables that is releasing very slowly. It is now 5 hours since the measurement ended here, so the tiny PFA has been idle for 5 hours. I don't think 5 hours is enough for this linear change to have stopped, so I have made some arrangements. So I have fastened the cable at some different points, so it will not move while I'm doing experiments here. I have started the new measurement, and I'm using this heat gun to warm the cables to release stress more rapidly. Here I was heating the thin cables near the tiny PFA. When I zoom into the region before I came close to those thin cables, here you can see what happened when I was heating the RG223 cables. I zoom out, it looks like this, and I will remove this and start again. As expected, the phase is drifting rapidly now. I can zoom into this region. But I expect it to be flat fairly soon now. It has been running for 1.5 hours now. The latest recording, which is here, is still not flat. It is a straight line, and something happens here. Well, that's normal. We have this, whatever it is. But I will reset and start again and do something else for 3 hours. The latest trace, the black one, seems to be good enough now. So I remove what I don't want to see anymore. So now the red trace is what I have with the long cables that I can now connect my amplifier. But before that I will zoom into a region like that. And here you can see I have quantization errors of some kind. I don't know what is the reason for this. Maybe some parameter change I did that isn't really optimum. Something had gone wrong with the output format, and I don't know exactly what, but I have reset and again set all those parameters that I intentionally had set before. And now it looks normal. And I will wait some time to see whether the phase is still flat over time. When I look at the Allen deviation, I can see now that the quantization noise is gone. The new trace is coming where I had the original blue trace. This is what it looks like when I zoom into the traces. This is 1 division per second, so I can see 0.2 seconds. The red trace is very different. It can take only 2 values, and for all this time it is at one of the values and then it is at the next. And they are separated by 1 times 10 to minus 13 seconds. So it is a very small time difference, but even so, this causes noise. Here is what I have seen now, the green trace. It has some low frequency variations, which probably is from the cables, but it otherwise looks normal. I can look at the Allen deviation, which agrees with the blue trace all the way up to 300 seconds or so, but at 1000 seconds it is not so good. And that is of course phase difference. 1000 seconds, it is 1 division here. So you have oscillations that are about 1 division long in the green trace. We also have that in the red trace, here for example, while the blue trace with the short cables is significantly better. And when I deleted the green trace, I see much better the big difference between the short cables, the blue, and the long cables, which is now red. A couple of hours have elapsed. I am now looking in monitor mode, and I can see that the phase shift is 10 to minus 14 with some number before, minus 7, minus 5, minus 8, it's minus 1. It varies a little bit up and down, but it is very small. So I make a new measurement. This time the stability was not good the first, 1 hour, 20 minutes or something, the green trace, but then it was reasonable. I will now connect the amplifier to see how that behaves. So here is what I see through the amplifier, and there is some structure here that is significantly different from the 2 other traces. I have zoomed in. If I zoom out, it looks like this. I can look at the Allen deviation, and we can see something happens above 5 seconds or so. And that's where I have the problem with sideband noise. So probably what I see is actually the amplifier and not the measurement setup. I will leave this running for some time, and then I will remeasure it a couple of times to see whether this is a stable finding or not. It's quite clear that the peak I see here at about 30 seconds, 0.03 Hertz offset, is reproducible. I made 3 different measurements the same way and they give the same result. Then I made one measurement, one of them with a 10 dB lower signal level into the tiny PFA. Means I changed the attenuator immediately before the tiny PFA, so nothing has changed for the amplifier I'm testing. And that has degraded a little bit at higher offsets because of the noise of the input amplifiers of the tiny PFA. But this, which is my main problem, has not changed.
Now this brown curve, which is slowly developing, the difference is that I removed the amplitude limiter, but it is the same signal level into the unit, so it is the same here, but it looks like something might be different here. I will have to wait for a while. It seems that the limiter is adding some noise at about 10 seconds. I can zoom into this region, and we can see the green and the bright green and the brown trace, which are the ones without the limiter. They are below all the other ones. And the one at the lower power level is a little bit higher here, although I'm not so sure that is significant. But it is very significant on this side, where the amplifier noise seems to be important. I have disconnected the second amplifier stage, and now I'm looking at the output of the first amplifier, the parallel FETs that are connected to the crystal. I have saved the blue trace, which is what I had with no amplifier in line, and then the two green traces are with the two amplifier, the upper one with the limiter also. I can magnify this most interesting region like that, so I can see that the results with the limiter, it is this curve, and without the limiter here. And now I have made 3 measurements, various versions of red, which is with only the first amplifier, and they are at short times significantly higher. I guess there is wideband noise because this amplifier has no selectivity almost. It's a very wideband tuning. But I can see that there is noise here that is larger than what I had without the limiter. The limiter seems to produce noise, and it seems, I cannot explain exactly why the level is so high here. One of the traces is a little bit lower. Anyway, everything is significantly above my test system. So I have noise also from the first amplifier. I want to measure the crystal filter without the amplifiers. So this is the circuit diagram. The bifilar transformer will step up the voltage by a factor of 2, means that the crystal will look into an impedance of 12.5 ohms. And that's about the level of impedance that it has with the FET amplifier. To do this, I have connected 2 amplifiers in series. Together they give 20 decibels of gain. And I have also put a 10 dB attenuator in front of the first amplifier while looking at the performance of the test system that I have, consisting of this amplifier, this attenuator, the 2 amplifiers in one branch and nothing in the other. And this attenuator is necessary because otherwise this one would be saturated at the signal levels I need to get good performance out of the tiny PFA. So with this arrangement, here is what I see. It is the bright blue. And it is a bit noisy, which we can see here, because the B channel on the tiny PFA has a very low signal level now. Now I remove that 10 dB attenuator and connect the device under test, my selective amplifier, instead. What I see now, the red trace, is very similar to what I saw with both amplifiers and the crystal. So this seems that the noise at 30 seconds originates in the crystal. Here I have decreased the power in steps of 1 decibel. And that changes the temperature of the crystal, I think. And the first step is fairly large, then they become smaller and smaller, because the power is lower and lower. So I have gone down by 1, 2, 3, 4, by 5 decibels, and I will look at what happens to the phase stability. It is obvious that the noise has increased now that the signal level is lower. That makes me suspect that the noise I see from 10 seconds up to 50 seconds or so is thermal noise in the crystal. I mean, thermal motion, also the crystals is shaking, and that will add phase and AM noise to this signal. So I will try to go the other direction and increase the power. Now I increased by 5 decibels, I am back where I started, and then I will go further. I have to zoom out. The step size is a little bit bigger, but not very much. Interesting, the steps become smaller. Maybe I am reaching the optimum temperature for the crystal. I have to step 10 decibels because I reached the end point of the attenuator. So now I should be back at the same, and I can make 1 dB again. And now the phase steps become bigger again. I think I go back 1. Here. And now I can adjust the frequency to get the same phase. That means I should get the center of the wrong direction. I need to make the tuning capacitor a little bit bigger. And then I will check that I really have maximum signal through the filter here. Now, with 5 decibels higher power, the result does not look good at all. I can look at the phase difference, and it's the black curve here, and you see it is clearly more noisy than the red one, which I made previously. And of course, we can see that better in the Allen deviation. So there must be an optimum somewhere, close to where I started. It seems that the original level, I call it crystal, was best at 10 seconds, 20 seconds, 6, these ones are 7, 30 seconds, best, and here this one is equally good. And here also. Well, statistics is maybe not good enough. It's 1.5 hours. But since the difference at 10 seconds is reasonably large, well, 7.8, 8.1, not very big. It seems that the original setting is that level I should use, and there was a reason I selected this signal level to start with, because that's where I thought the sideband noise was best. At this time I turned the potentiometer for the thermostat a quarter of a turn counterclockwise, so the temperature went, I don't remember which direction, and then here the phase had its extreme value, and now it is going and beyond the value I had to start with. So the correct setting is fairly close to the original, but a little bit counterclockwise. So I try to adjust until I get this phase shift, or close to that. At this point I turned it towards getting warmer, and here I have set it at some point where it might be close to correct, so I run it clockwise to close to the original. And now I can see on the current consumption it is cooling. Well, I forgot that the power is now 2 decibel higher than what I think is the optimum, so I reduced the power by 2 decibels. And then I check again by setting the temperature a little bit too high and wait for where the new optimum phase comes. Now this is pretty close. There is a minimum here, and the temperature is going past it, but not very far. So I will look if there has been a difference on the Allen deviation because of this. I mean, is there a thermal noise due to a bad thermostat, perhaps? This is odd. For all I know, the only thing I have changed between the old measurement on the crystal is that the temperature is a very small amount higher than before. The first measurement is the red track, and it looks bad here. I then looked at everything and moved the cables very small amounts, waited for a while, and now I run this brownish trace. There's a lot of noise at short times, but here, maybe not, it is significantly lower. When I look at the phase, it is clear that the brown trace has a lot of high frequency components. The red trace has very little. And, well, there is a fast change here. So I'm confused now. I'm looking at the current through the thermostat, and here is the voltage. The voltage is very stable, but the current varies a little bit up and down. Here I have moved the trimmer a little bit and then set it back. And then I have these things. And here I moved it back and forth quite a lot, several times. And now it looks like this. And I can see no correlation between where the phase is and what the current is. This big change in the phase shift through the amplifier or through the filter is not because something I did, it just happened. And I think there was a small change in the thermostat current. So I will switch off the thermostat and see what happens then. Well, this is odd. As it is cooling, it makes jumps. And here, and here. So there is something funny with the crystal. This is not what I had expected. Well, I will leave this running for a while. So the crystal obviously has two modes, and as the temperature goes down, it switches between those. Because now there is no current through the thermostat, and there is nothing, no voltage applied to the box. So the only thing that is happening is that temperature is going down. I will adjust the tuning because the signal I have is drifting out from the center frequency of the filter. It seems the artifacts jumping between two different modes has stopped now, and the temperature must be going down slower after this time, but the curve slope is increasing. So I'm getting further and further away from the sweet point for the crystal. Well, sooner or later it will stabilize, and then I will have a look at the noise. Now I have reached the minimum capacitance of the tuning capacitor, so I cannot follow it anymore. But I will wait and see what happens. The frequency is drifting downwards of the crystal, and I cannot follow anymore. So when measuring phase shift, it will be off resonance, but still I think that will tell how the oscillator would behave. Well, here was a phenomenon. I can magnify it, so it is misbehaving also at a much lower temperature. And here was a major event. Well, now things have become stable. Although these big phase jumps, they don't look nice. Anyway, I cannot do any measurement now because the signal level is about 30 decibels below normal. And I cannot adjust the frequency because the tuning capacitor is already at minimum. So I will go the other way, since I was on the peak. Normally a crystal has a characteristic like this. It goes up and then it goes down and then it goes up. So I was sitting on the peak there. I will switch on the thermostat for a significantly higher temperature to see whether I can see the minimum that is supposed to be at a somewhat warmer than I had before. The temperature is rising. There have been events here, the strongest one, but here also. And there were several before I started the measurement. And here, one again. So I will wait for a while to see how the curve behaves. Because I expect it to have a minimum and then go up again, and then have a maximum. The signal level is decreasing. I have passed the maximum, so I will increase the tuning capacitor now. So now the signal level is restored, but it's still drifting downwards. Here the maximum frequency is passed. I will magnify this section. And you can see there are these irregularities. And just at the point where one normally would operate, or where I have been operating it, at the minimum here I have this. And this could explain why performance was so bad. I expect the frequency to reach a peak and then go down again. But maybe I will have to, well, the power to the oven is still maximum, 408 milliamps. I think I had 160 milliamps before. So it is rising in temperature, but the phase is not changing very rapidly now. Well, here is a maximum. So this is the appropriate operating point. The power to the thermostat is high. I will turn down to try to stabilize at this point. The temperature is still rising, but the current through the oven is not very high now. It's 160 milliamps. That was appropriate for the previous temperature. But the temperature is too high, so I will probably have to reduce a little bit more. Now the oven power is stable at 3.8 watts, but the temperature in the crystal is still rising. Well, here is the maximum, so I have to reduce the power a little bit. What I see now are these curves. They go high above the first one I had, the blue curve. When I look at the phase difference, it's obvious. Something happens here, and that is not random noise. There's some event. Otherwise, this black curve looks fairly nice. Here I have started a new measurement, and here I have a strong magnet, and I put it close to the crystal here. And this is what happens. And I don't know the reason for this. Something is moving inside. And this explains why, when I switch off the thermostat, which I will do now, I see something. That is the current coming and going. I switched it on again because I want to have the thermostat running. It seems to me the explanation could be something is moving inside, something that shouldn't be moving. The output impedance of the crystal filter in this box is close to 50 ohms. Now I'm feeding my test signal directly to the amplifier without going through the crystal filter. To do that, I have put a 20 dB attenuator in front of the box to get the normal signal level that would cause about 3 decibels of amplitude limiting if I connect also the limiting diodes. They are not connected now. So I measure it now. And the blue trace is what I had with the 2 amplifiers and the filter. The red trace is my test system with nothing as the device under test. And it is seen fairly quickly that this new black trace goes below the blue trace when we come up to something like 10 seconds. Already after 2 minutes, it's quite clear that the main problem is the crystal. It's obvious at a time scale of 100 seconds or more
there is a phase instability in the amplifier for some reason. And it's clearly seen here in the phase plot. Something is oscillating a little bit, and the time scale is from here to here about 3,500 seconds an hour. I have started the new measurement, and now I do like this. And it's obvious that something has changed, the temperature, and the internals is cooling off slowly, and then it will probably turn and go back to the room temperature with some fairly large delay. This is what happened when I waved a sheet of paper. And this is the measurement that I made over 3 hours. So this could perfectly well be the temperature varying. And as you can see, the problems arise above 10 seconds of my rather brutal temperature change. I have installed the amplitude limiter, the 2 crossed Schottky diodes. And I compare with the various things, but first I magnify the interesting region to see better. So the blue trace is the FET amplifiers without the limiter and without the crystal filter. The black is the FET amplifiers with the amplitude limiter and the signal level set for 3 decibels of compression. The red trace is with 5 decibels of amplitude compression. The dark green trace, that is with also the crystal and with the amplitude limiter, while the bright blue here is with the crystal filter and the amplifier, but without the amplitude limiter. And it's quite clear, this observation I made earlier showed that the amplitude limiter is a problem. Now I see that much more clearly. The amplitude limiter is not good. When I look at the phase shift from input to output in the time domain, I can clearly see that the FET amplifier only has this temperature-caused variations, probably temperature, but no higher frequencies, unless this very fast white noise. And with the 3 dB amplitude limiter, there is much more noise with lower frequencies. I guess it's flicker noise in the diodes. And with 5 dB compression, that noise is significantly bigger. Something has gone really wrong now. The red trace is my test system without the amplifier. The blue trace is what I saw with the crystal filter but without the amplitude limiter. And the bright blue is the same but with the amplitude limiter. So I see clearly a contribution of noise from the limiter. But the red is when I try to reproduce the blue trace now. And the green is at somewhat higher power. The input power to the amplifier was 9 dBm for this trace and 11 dBm for the green. So something is really wrong now. As it turns out, it is one of these potentiometers. This is what I use in the box to adjust the current through the thermostat, or rather to adjust the thermostat temperature. This is a wire-wound
potentiometer, and when turning the screw here, one has to be very careful to place it on one of the turns of the wires that make the resistance. If it comes a little bit on the side, it is noisy. I have adjusted the temperature control trimmer carefully to come exactly at the point where the derivative of the frequency versus temperature is 0. Now I cannot come exactly correct because of the step function of the trimmer potentiometer, but this is the group of curves I have, and I have tried at different input powers into the box. The power is a little bit higher now than before, and it isn't dramatic what happens. Something is statistics, but it is clearly much better than it was before the blue trace. I will add some fixed resistors to make the sensitivity of the potentiometer much smaller. Now I've got a problem with the stability of my setup. I can no longer reproduce the nice trace I had here. Does it with nothing as the dies under test. This blue track is what I had with the crystal filter and the amplifier, but I have seen very good results with the crystal and the amplifier now very recently, but no longer. So now I have connected nothing again, and this is the instabilities I see. And I've tried a little bit different IF frequencies, because I'm not quite sure what I used when I made this nice background. This is the USB connection for the tiny PFA, and that is another cable going to here, where I've connected the screens together with the screen from the USB cable, and then I'm looking at the ground and the +5 lines. And here is what I see. Fairly strong signals, and the same on ground and on +5 volts. And at a slower speed I see a more complex structure. I have inserted an extra cable of the USB, and this one does not have any connection with the screens. There is no screen in this extra cable I have inserted. I have placed a big capacitor between the 5 volt and the ground line, or rather the negative line on the USB cable. What I then get is the black line you see here. Without that capacitor I had the blue line here. And this, which is now blue, is what I had before when I was running with no amplifier, just the test system itself. And this is the old measurement with the amplifier, with the crystal filter. I have permanented the USB grounding, including the grounding of the screen. I have used this hybrid to send the same signal into both ports of the tiny PFA. I have spent a lot of time trying to get back the performance I had originally, which is the blue trace here. Even though I am sending the same signal into both ports through the hybrid, the curves have been in the range here about. And I have changed parameters and seen small improvements. And then, the magic thing, I have added filters to get rid of overtones to 10 MHz. And that made a big difference. So I added these two filters. They give about 60 decibels attenuation on the second harmonic and much more on the higher harmonics. The important parameters on the tiny PFA is to set the large tau half a second and decimation 1. The lowest IF frequency, 4 kHz, gives the lowest noise. Note that the level is indicated to be 7 dBm up here, but if I set the normal IF frequency 24 kHz, then it indicates 5 dBm. So I don't think that is any problem, because the front end is the same in both cases. It's something with the software. The brightness should be set to minimum, and I have switched off the traces on the screen to have it as quiet as possible, because the changes in current in the unit changes the phase that it measures. This is important. If power is set to auto, then suddenly it changes between the different levels. I guess it's the charging of the battery. And when now and then there is a step function on the recorded phase, and that destroys the Allen deviation. So fixed minimum, that helps to make the system more stable. And I don't know what pull is doing, so I have not changed it from the default. I now have only the test system, so the amplifier is not connected. I have just these BNC adapters. And what I see here is very close to what I had with the power splitter. And then I don't know what this means, some instability. But it is much better than what I had before, because the filters and also because of better settings for the tiny PFA. So I will allow this to run for 3 hours and see what the result becomes. This looks good. This is with all the cables, the green trace, and it's about the same as when I had just the power splitter very close to the tiny PFA. This is a typical frequency response for these crystals I'm using. They are intended to be used in a thermostat. There are 2 points where the temperature sensitivity is small, at this top and at this low point. So this is cooler and this is warmer. I don't know exactly how many degrees it might be, but maybe 90 or something here, and this is cooler. I have a thermostat with 6 1N4148 in series, and the voltage across all of them is 2.3115 at the top and 1.8866 at the low point. And this is the thermostat. So I feed these 6 diodes from a 5-volt source through 33 kiloohms. So it is possible to look in the data sheet and figure out about where the temperature is. Here is the instability of the phase shift when I measure at the temperature for the top, the cooler temperature. And I have tried 10 dBm input, 14 and 16. And clearly 16 dBm, the green trace here, is not very good. I am particularly interested in the region from about 5 seconds up to 30 seconds. So if I look at the 30 seconds, I find that 10 dBm gives about 7 times 10 to minus 15, and 14 dBm is better. It gives about 5.5, and I measured 2 times to see how much they differ, and they don't differ very much. But at 16 dBm, the noise is much higher, and at 30 seconds I see 8 times 10 to minus 15. And at 10 seconds it is even more clear that 16 dBm is too much power. Now I think this may be the amplifier that gets saturated, but that's a problem I will look at a later time. At the higher temperature, T low, I have 14 dBm seems to be too much power. But the other traces are reasonably close to each other. 10 dBm, 8 or 9, or 8 here. And 8 or 10 dBm don't differ very much. These curves are a little higher than what I see at the lower temperature. So low means frequency, not temp. Here I compare the two sweet points for the crystal. T low means the higher temperature is a little bit above 1 times 10 times minus 14, but the lower temperature is about 8.6 times 10 to minus 15, and that is at 10 seconds. And what happens at higher, longer times is not so interesting. What is interesting is this region. And here it is clear that 2 traces are higher and 2 traces are lower. And here is the test system when there is no amplifier, just BNC to BNC female connectors. The 2 upper traces, they are with the crystal, as you can see here. That is the optimum condition for crystals, 10 dBm power and the lower temperature sweet point. And then I have bypassed the crystal and measuring only the 2 amplifiers at 10, 14 and 19 dBm. 19 dBm causes some compression, and it gives this green curve very high above what I have at lower power. So this I just skip it. So here is 2 traces with the crystal, and here are traces with only the amplifier. And at times below 10 seconds I cannot really see the noise from the amplifier. So problems arise from the crystal and sometimes due to compression in the amplifier. What remains now is to make a good amplitude limiter. I have made an amplitude limiter like this, you can see here. The final amplifier down here is disconnected. I have cut here, and I have placed an extra pickup winding on this coil, where I look with the tiny PFA, and I can measure the voltage here also. The secondary winding is a bifilar one, 2 well-twisted wires, 4 turns, and then 39 ohms to the basis of this transistor, and the 27 ohm resistor between the bases. That's to bring down the voltage because it's a bit too high here. And I want resistive things near the transistors because otherwise they become oscillators in VHF region. And that's why I have this 47 ohm resistors. This also. I zoom in a bit closer, and we can see at 1200 seconds about it starts to flatten out. But there is noise here. So I will start measuring the Allen deviation now. And this is not the first experiment. The blue trace here, that's with nothing. That means only the cables. And the red or magenta trace up here, that is with the crystal, plus the amplifier, but no limiter. The green trace, that is with the amplifier, but with no crystal. And then the red trace, close to it, it is the limiter that you just saw the schematic for. And it is very close to the amplifier only. And that is with a voltage of 2.76 peak to peak on the 4 turns winding. Then the light blue up here, that is with 4.32 volts, means less losses, a bigger resistor parallel to the output. And that is no good. And here the brown trace, that is with 3.56. And right now I'm measuring with 2.76 volts. That's the same as I had for the red trace. And it doesn't look so promising. It turns off here. But that's just the beginning. I will have to wait some more time. Looking at the phase difference, it seems that it hasn't stabilized yet. So I will have to wait some more time. It looks a little better now. I can zoom into it. And you see it is this green trace and it bends down, and now it is here. Looking at the phase difference, you can see here it really is drifting significantly, the green trace here. So I will wait another half an hour. I made the latest track black so it is easy to see, and it is obviously the best. If I look at 50 seconds, it is at 7.1 times 10 to minus 16. Now, what I have here, those lines that say lim as something, they are at the output of the limiter. So that is what is going to be sent back to the input to create oscillations. And it's obvious that the voltage on the second stage has to be pretty low. It's now 2.76 volts peak to peak. Now I had that before at the lower input level, means I had higher gain. And that was not quite as good. Probably because at the higher signal level, thermal noise or the noise figure of the amplifier is less important, so I get a better performance. It seems to me that this limiter is close to ideal, so I will stop investigating it separately as I am doing now and go for some other aspects of this thing. I have removed that 4 turns pickup coil, and I can measure the voltage on this point instead. That is also 4 turns. And I have connected the buffer amplifier, and I had to put the 470 ohm resistor here to not overload this amplifier. And that gave me a voltage of 2.05 volts at this point, which is pretty close to what I had before, just a little bit below. And that is for a 14 dBm input, and that gives me an output of 18 dBm. What I see now is not good at all. I made the trace black to easily see it, and it is high above what I had from the preceding stage, the red trace here. So I will try to reduce the signal level to see whether that is the problem. Something is really wrong now with the final stage. It is this black trace here. What I see is that the phase shift through this amplifier is unstable. And the only thing that is suspicious about it, as I can see, is this transformer. It's a bifilar thing. What happens with it is that the current through all these 12 transistors is going through this winding, through the transistors, and through this winding. That means that I have 50 turns with all the DC current that goes through the transistors. And that might give a problem with the iron. So I tried to reduce the number of turns to about half, and that made absolutely no difference. I have prevented the current, the DC current, from going through those windings by putting chokes here and here to have the current going this way, and then coupling capacitors 0.1 microfarads here and here. This made some difference, but not at all the full performance that I expected. I have made 2 measurements, both about 1 hour. And the biggest difference is in this region here. I didn't save the previous one, because I didn't think it was so interesting, but I regret that now. When I look at the phase versus time, phase difference versus time, it looks like this or like the blue one here. So it is noisy very clearly. I have reduced power by 4 decibels. Didn't make much difference. It's the black curve here. At short times, 10 seconds, I have lost a little bit in performance. I guess this is amplifier noise that starts to be visible when the signal level goes down. But here at longer times it's about the same, and at very long times the statistics is poor because I have not measured long time enough, about 1.5 hours only. I have moved the cable from the normal output to the limited output, but that didn't make any difference. It's the red trace you can see here, and it's high above where I want to come down here. I have cut the connection from the second to the third amplifier and moved the load resistor, which was sitting here, to be here instead. So now I should see the same result that I had before when this was not connected. And indeed, that is the case. I am now measuring this blue trace. You can see it's ticking up there. It comes here, very close to the brown trace, which was the one I made some time ago when I studied the limiter. So nothing has happened to the limiter. The problem is the third amplifier stage. And since when I had this connected, the phase shift with time that I observe is the same when I look at this output or when I look at this output when this was connected. And that tells me that the capacitance here, looking in here, is changing at random for unknown reasons. I don't think it is normal. It could be a bad soldering or a bad transistor, or maybe too many FETs like this do have this kind of unstable input capacitance. I don't know. I will try to find out. I have disconnected this inductor, so there is no current through the transistors now.